Well, maybe we'll kick things off here, and people are continuing to join. It's a real pleasure today to have a longtime friend and colleague speak to us, and this is Dr. Rob Jeffrey. And prior to joining CSIRO in 1989, Rob worked for Dowell Schlumberger and for Schlumberger, and there he worked on hydraulic fracturing, and the emphasis was on fracturing of coal bed methane wells. He continued with this research at CSIRO and ran a range of projects investigating hydraulic fracture mechanics in coal and in naturally fractured ore bodies. So Rob was instrumental in introducing hydraulic fracturing to the mining industry for cave inducement and preconditioning of rock masses. This technology has been used at mines in Australia, Chile, Sweden, China, and Indonesia. And in 2025, Rob received the SPE's Legends of Hydraulic Fracturing Award. So congratulations for that, and welcome, Rob.
Thank you, John. As you can see on your screen, I hope the title is Hydraulic Fracturing in Mining. And as I get going here, I intend to describe how fracturing is used in mining, which is primarily in the areas of cave inducement and preconditioning, both in coal mining and metal mining. And I'll point out how some of the aspects of fracture growth that we observed while doing that preconditioning are related to what's seen in both shale gas and geothermal fracturing, where we have closely spaced fractures that are extended transversely from the borehole or well. And we see quite often, for example, also asymmetric fracture growth with respect to the well. Aspects of using fracturing around mines that we can take advantage of, or that we can usually put in extra monitoring, and we can sometimes carry out mine back operations to map the fracture as placed, or at least the propped extent of the fracture, and see the details of how it grew through the rock mass. And finally, I'm going to present some data showing the pressure loss associated with the reorientation of these fractures if they initiate axially and then grow transversely. There's quite a bit of complexity in the fracture geometry that is near the wellbore, and that is associated with a large entry loss. So to start with, I'll introduce this slide, which summarizes what longwall coal mining is for those that aren't familiar with mining processes. So in the upper left is a diagram of an operating longwall mine, and in the lower right part is a photo showing a longwall shearer cutting coal along the longwall face, and it operates in a protected zone where the roof is supported by hydraulic supports, which are the large objects to the right of the photo. And you can see for scale, there's a miner standing here looking up at the shearer. The seams in Australia tend to be quite thick. This is probably about a 4-meter thick seam. So the scale of the equipment is quite large. But the reason for showing this diagram in the upper left part of the screen is so I can talk about how the longwall operates, but also how the rock strata behaves as mining progresses under the roof. So the longwall is shown here in the front part of the image, and a zoomed in view of the central part of the longwall is shown in the upper part of the image. And you can see the red square objects along the face here are the supports. So they've been removed graphically in the center portion to expose the shear operating across the face, taking slices of the coal seam about 1 meter at a time as it traverses back and forth across the longwall panel, which can be more than 300 meters in width. And entry to this longwall face is obtained through roadways driven on either side of the panel. And also these provide a way for air to enter, for ventilation, and for the coal, which is placed directly onto a conveyor at the face and conveyed out to the end of the face, where it's run through a crusher and then put on another belt and taken out of the mine, which you can see more clearly perhaps in the upper part of this figure. So the issue with that hydraulic fracturing addresses is that if the strata has a strong roof rock that is immediately above the coal, that is especially the worst condition when it's immediately above. And if that roof is strong enough, it can stand up for considerable distance as it's undermined. So instead of caving immediately after the supports, as shown in this diagram, it may stand up and leave a void underneath it. And that presents two problems. One is when it finally comes in, it may come in very quickly and displace any gases that are in that void, creating high velocity wind blast risks in the mine workings, with wind velocities recorded of several hundred kilometers per hour. And also those gases tend to contain methane and CO2, which can result in displacement of explosive or suffocating gases into the mine workings. So that's obviously to be avoided. The other factor that occurs is, even with a small amount of overhang, the extra weight of the roof on the supports can overload them as they start to fail. And then the steel supports can be hydraulically overloaded so that the cylinders are pushed back in, or the pistons are pushed back into the cylinders of the supports, and the roof converges dramatically, and the coal face tends to get crushed at the same time. So you end up with broken coal filling up the face area, and the supports are no longer effective, being pushed down to their shortest extent. And it can take the mine weeks, if not longer, to dig itself out of that condition, costing typically millions of dollars, if not tens of millions of dollars. So that's a second problem that they want to avoid. And preconditioning and cave inducement, depending on the situation being addressed, have been introduced into coal mining to weaken the roof rock and avoid those conditions. And here's a photo, and I'm going to talk briefly about this case study at Mooney Colliery in New South Wales, which was an underground coal mine with a strong conglomerate roof. And that roof would stand and leave open voids for hundreds of meters behind the mining, and then would cave suddenly, producing severe wind blast. And one aspect of that can be seen by the safety equipment the miners were required to wear: full full coverage motorcycle helmets and goggles, leather jackets, knee protection, and they also had straps attached to a belt harness that they could attach to heavy equipment to prevent themselves from being blown down the tunnel if a wind blast occurred. So they had microseismic monitoring in place that would give warning of a wind blast, but it also gave false alarms. And of course, it wasn't a pleasant working environment if you had to rely on jumping into a safe haven and attaching yourself to a piece of equipment as your last resort. So at that time, this was 1999, I was working at CSIRO, and SCT was approached to address this problem, and they contacted us to work on this project with them. Ken Mills was the primary contact there. And with the mine, we came up with a method of putting fractures into the roof from underground that would induce caving and prevent the wind blast from developing. The mine found that if the hanging up roof was less than about 40 meters, the wind blast was not severe enough to cause them any problem. So they could drill holes when the face was located as shown here, drill vertical holes up to about 8 to 10 meters into the roof, then install an injection pipe into that with a void at the top, and connect a high pressure hose to that injection pipe. And then as they mined the next 40 meters, they would trail the hydraulic hose through the supports into the void behind. And then at this point, they advanced 40 meters and they can create a hydraulic fracture in the roof to induce a caving event. And they used that successfully for the rest of the mine life, and it managed to save the mine, which was on warning from the state safety people that they had to find a better solution to their wind blast problem. So we did build a model that with Tony Satari that accounted for the free surface near the fracture growth. And we were able to calibrate that model with direct measurements of fracture growth with offset monitoring holes installed into the roof, with instrumentation then trailed through the supports also and connected to logging devices. And here's a record of the recorded injection pressure in red, the modeled injection pressure in green, and the modeled fracture growth with the open blue squares. And the one point we had to calibrate the model to was a solid blue square at about 15 minutes into this treatment. So the common aspect of these treatments were that they started at fairly high pressure to break down the open hole in the roof, but the pressure then fell quickly, indicating fracture growth and opening of that fracture, with the fact that there was a free surface less than 10 meters away, allowing the fracture to open more quickly than normally would be seen in a deep fracture. And then eventually the injection pressure would fall down to half an MPa or less before a fall would be induced. And here's a very graphic result showing the effect of the fracturing on mining at this mine. This is a plan view looking down on the panels with the recorded size of each fall event shown in a different color. So for the first two long walls, longwall 1 and longwall 2, and the long walls are 100 meters wide, the size of the falls varied quite dramatically. These were not controlled falls. They just occurred whenever a weakness occurred or conditions were right to produce a fall. So you can see the quite a few of the falls were small enough to be no problem, 30 or 40 meters or less, but a large number of the others were 100 meters or more and produced severe wind blasts. And the lower part of this shows longwall 3, the last part of longwall 3, where hydraulic fracturing was being used to induce falls that were on average about 40 meters and did not produce significant wind blasts. So that was a very successful project that introduced hydraulic fracturing as a way to induce caving. A second example in coal mining is shown here, which is at Narrabri mine, also a longwall in New South Wales. And in this case, again, they had a strong conglomerate roof rock. And to start with, their primary worry was that during startup, they didn't want a large standing roof. They hadn't, this was a new mine at the time we introduced fracturing, and they knew about fracturing from Mooney. So they were looking for a way to weaken the rock and ensure it would cave normally and not stand up for a large distance, creating a gas displacement risk to the mine. Again, this was a project done with SCT, between CSIRO and SCT. And we ended up putting a row of boreholes across the face, which was about 300 meters wide. And we put a borehole every 30 meters or so across the face and put fractures that were designed to be at least 30 meters in radius and closely spaced into those boreholes to precondition the rock before the mining had started. A new longwall face is started by driving a tunnel across the face and then installing the supports and longwall shear at the face, and then the system is started and the longwall advances to the right, leaving a hopefully caved roof rock material behind it. So in order to verify we were getting good preconditioning, a primary concern was, could we put hydraulic fractures in at 1.25 meter spacing and extend them to approximately 30 meters as parallel fractures without them diverging or converging. We had stress measurements that indicated that the fractures would be horizontal, most likely, but this monitoring method also let us verify that we were creating horizontal fractures. In addition, we had surface tilt meters, which also verified the horizontal fracture growth. But the way this worked is that the monitored borehole, which was the next one to be fractured, was filled with water to the surface, and then before fracturing, the lower portion of it was filled with cold water, and a temperature sensing string with discrete temperature sensors was run in to cover the area where the fractures should arrive. So when the fracturing occurred, the hydraulic fractures grew across and intersected that cold water filled borehole and caused an increase in temperature at the arrival point, that allowed us to determine the time of the arrival. So we got a rate of growth, verify the fracture was horizontal, but also, more importantly, locate the depth. So we could log the initial depth of the initiation and the arrival depth and verify we were producing parallel fractures. So in this figure, we show the result of one set of those logging exercises where the initiation points and the frac hole is AM. And these are the initiation points shown here with straddle packers used to isolate each interval. And we pre-slotted the borehole to try to control initiation. So we start at the bottom and place the fractures from the bottom up. In this case, all of them were essentially parallel and propagated across the 30-meter distance as parallel, closely spaced, except for the second fracture, which somewhere along here merged with the first fracture and arrived at the same location as the first fracture. So this was a successful monitoring exercise and confirmed the quality of the preconditioning. And here's a record recorded from one of those boreholes where the temperature varies as a function of time. And before arrival, there's some up and down movement in temperature along the instrumentation string. But after the arrival, we see a very sharp increase in temperature at that depth, which continues to develop with time. And you can see the warm water that's displaced into the borehole moves up the borehole because the collar was open of this borehole, so the fluid could move out of the borehole. And therefore we get a warming of the borehole above the depth and not as much below. And we can still locate it even fairly late after the arrival. We can locate the depth of the intersection point. So we set out to precondition the rock so that they wouldn't have a void. They did develop a void of some 24 meters, but they had a limit of about 24 meters on how far they could mine before they would have to stop and reconsider how to continue mining if caving didn't occur. But caving did occur at about 24 meters and continued on from there on as they continued to mine. So from that point of view, it was also a success. And the mine continued to precondition ahead of the mine for the rest of this panel. Now moving to hard rock mining, preconditioning and cave inducement has been used in block caving and sublevel caving as a way to weaken the ore body and ensure that caving occurs as designed. Briefly, I'll just go through how block caving works. This is a diagram representing block caving as carried out at Cadia East in New South Wales, which is a gold copper block cave. The idea is the ore bodies are quite massive, so maybe 200 by 200 meters of footprint is undercut and developed at a time and then extracted. And typically a lift here might be 400 or 500 meters high, with the requirement being that you develop a system of tunnels underground before you start caving. So you drive a transport level or a conveyor level. You have a crusher system, and you have a extraction level where the ore is is extracted from the draw points and carried over to the grizzlies and put into the crusher and then taken out of the mine. And these draw points are everywhere located underneath where you want to extract ore. Historically, block caving mines have been used to mine ore that was weak enough so that if you developed an undercut level, which is just on top of this draw point system, you can undercut the ore body by driving tunnels and then blasting the first 20 meters or so of the ore body to rubbleize it. And then as you start drawing that ore out, the lack of support that is produced on the overlying ore is sufficient to cause these weaker ore bodies to cave continuously. So as you draw the ore out, the ore caved, and you could continue mining without any additional effort. However, those weaker ore bodies have mostly been mined, so a lot of the newer ore bodies have stronger ore that requires something to be done to it in order to weaken it. And that something is place hydraulic fractures into it in many cases. So here they developed a system of tunnels to allow placement of the drilling of the boreholes and then placement of the hydraulic fractures. So they drilled perhaps 20 or 30 boreholes over this area and placed hundreds of hydraulic fractures into each into the boreholes at spacings of 2 to 3 meters to precondition the rock mass for caving. And this hydraulic fracturing level was located 400 meters above the undercut level. So this isn't to scale. In another mine, North Park's E26, this was the first example of hydraulic fracture being used in Australia to induce caving in a block caving mine. And here you can see a hydraulic fracture being placed using straddle packers near a cave back from an offset or existing tunnel that allowed access to existing boreholes or drilling of new boreholes to place the fractures. And that process was undertaken in North Parks because initially they undercut it and started mining, and they thought they would be able to mine without preconditioning, but preconditioning really wasn't a thing when they started mining here. But after completing the undercut, they found the caving wasn't keeping up with the extraction, so they were generating an air gap above the broken rock, which is undesirable because it can create a wind blast. So plus it limits the amount of ore you can extract. So they contacted us. Andre Van Os contacted me at CSIRO, and we took our equipment there and from underground did a series of campaigns to cave induce and precondition further away the rock mass for caving. And eventually about 8 million tons of additional ore was caved by that method. And for the next ore body at North Parks, they preconditioned it from the surface. So in this case, vertical boreholes were drilled from the surface. The ore body's extraction level was at about 580 meters below the surface. The preconditioning was carried out to about 400 meters deep. And the top 80 meters was not preconditioned because it was weathered rock. But the design was to drill vertical boreholes and then place a series of closely spaced hydraulic fractures along each borehole at 2.5 meter spacing, with the borehole spacing being 50 meters from borehole to borehole. So this is a plan view of what the array looked like and the elevation view. And during that fracturing, we found that the fractures were not always symmetric, as shown by this sketch to the left here. So quite often, or nearly every time really, the fractures would interact with each other or with changes in in-situ stress or rock properties and end up being non-symmetrical about the initiation borehole. So you end up with a more uneven fracture spacing and preconditioning effort, if you will. So this is undesirable, but it's currently just a fact of life as far as being able to reduce it. You can pump more viscous fluid to try to reduce the asymmetry, but then you end up with, first off, the extra burden of mixing gel and pumping gel, but also you end up with higher interaction pressures between the previous fractures, which are still containing some gel, and the new fracture placed next to them. So it's not clear if you're going to improve the condition or make it worse by doing that. So these are all done using water. We did have the opportunity to do a mine back, actually a couple mine backs at North Parks before preconditioning E48. And this was one of them done in a decline tunnel that was driven to gain access to the extraction level of E48. So before the decline was driven, which is a tunnel approximately 5 meters by 5 meters in cross section, we put a couple hydraulic fractures ahead of the decline in a borehole. And then when the decline was driven, it exposed those fractures and we mapped what we saw. And this is the sketch showing the extent of the fracture that had red plastic proppant placed into it. So the red part of this sketch is the plastic proppant mapped on the wall of the decline, where the tunnel wall is the wall facing into the far side of the tunnel, and the borehole from which this fracture was placed was another 15 to 20 meters into the rock behind the wall. The dotted line is where there was a fracture present, but no proppant. And this part up here was a sheared fault or a shear zone where we could see slick-and-sided material in the fracture, and it was fairly easy to map the fracture even without proppant. And the hydraulic fracture followed that down to about here, and then it stepped out of it and propagated through unsheared rock along here. And at about this point, the fracture went up into the roof and we couldn't map it any further. The next, well, you can see overall here, we got a number of offsets along the fracture, usually at places where the fracture interacted with natural fractures. And we got a few small branches in the fracture developing. The next slide shows a photo taken at location P1. So here's what it looked like in a in a photo, quite a close-up photo. This is the main fracture channel that continued off to the left and right, and this is the branch that was shown in the previous slide. And you can see, for example, here the fracture grew along a natural fracture that's dipping across it here and then extended on. And it has quite a few little features, offsets, roughnesses that occur along its path as it grows through this naturally fractured rock. The rock mass at North Parks is a hard volcanic sediment that's been metamorphosed, and it's contains about 5 natural fractures per meter that have been mapped in detail along tunnel sides. So here's a photo taken at the face of the decline as it was being driven, showing again the red propped fracture. And you can see some small offsets here developing as it grew through this subvertical set of natural fractures. And just to remind you what the overall shape and extent of the mapped fracture was, the fracture extended as a prop fracture for more than 25 meters, but no doubt went quite a bit further as an unpropped fracture. But once the proppant is not present, it can become very difficult to map fractures since they tend to look like any other fracture in the rock mass. We did a study of what the effect of offsets might be on fracturing pressure and growth. And we did that with an idealized model of a stair-step fracture, as shown here, where the steps in the fracture path were 1/10 of the length of the main step. So we had 4-meter steps and then 0.4 meter risers, if you will. And we put a number of those in and varied the angle that they existed at and ran those through Shi Zhang's 2D hydraulic fracturing model based on displacement discontinuities. This model considers viscous, fluid flow, and frictional sliding contact interactions and propagation with fluid lag and fracture toughness considered. So the real fracture geometry beam model, without exaggerating these risers, is sketched here just to show a more realistic representation of what we were considering. And here's a result showing fracture opening with position at various times for that simulation. The brown curve here is for a straight fracture without offsets. And for a comparison, at 87 seconds, that had extended to 20 meters either side of the injection point. Whereas at 86 seconds with the steps, you can see this purple colored, pink purple colored, shows the opening for that case with the first step here, creating a restriction in width and producing then higher pressures upstream of it, producing this much larger opening and restricting the opening on the downstream side of it. But the fracture had grown to about 7 meters either side compared with 20 meters for the straight fracture. And finally, at the end of the simulation, 347 seconds, the blue curve. The interesting thing is the fracture was still high pressure at the center because of these restrictions. For example, at the second set of offsets, but the first offset had opened to actually be wider than the straight fracture at that point. So essentially, it was no longer offering a pressure restriction. It still had a width restriction there, but not sufficient to produce any pressure drop. So that's the story, basically. These offsets produce restrictions in opening and higher pressure upstream, and they retard fracture growth. So the fracture only ended up being about 12 meters long either side for the offset fracture after 347 seconds, whereas it grew to 20 meters in 87 seconds for a straight fracture. And here's a graph showing that effect. So this is the fracture half length versus time for a case where beta was 60 degrees, which is the angle of the offset. And you can see the retarded growth as a function of beta, 60 degrees here, 30 degrees here, and 0 degrees here. So this is a straight fracture. Now this effect, of course, is strongest in a 2D model because all of the fluid is forced to go through each offset, but it provides a useful concept for understanding how offsets affect pressure if the fracture crosses them somehow, which we see in minebacks it does. Then there's an effect there for any flow that has to pass through the offset, but also even if the fracture grows around the offset feature, it has to follow a longer flow path, which will result in higher pressure, though not as extreme as shown here. And finally, talking about the issue of asymmetry. At North Parks, we did a couple trials which involved putting monitoring holes around a central fractured hole and then monitoring with temperature logging and pressure monitoring the arrival of the fracture or not arrival of the fracture at these monitoring holes and confirming the depth location so we could get dip and orientation of the fracture. In addition, we had CSIRO provided surface tilt meters and analysis of the fracture shape from the tilt meter analysis, inverse analysis. So these circles are the best fit of the tilt meter shape produced to the monitored data from the monitoring holes. And then we could use that same tilt model to monitor the rest of the preconditioning. In this case, the fractures were dipping. We measured 17 degrees to the east, but I say here 15 to 20 degrees because there's always some variability. But the important thing is that this clearly shows the development of the asymmetric fractures developing in the rock as a result of fracture to fracture interaction and interaction of the fractures with the natural fractures and with the stress field. So we see this over and over again wherever we carry out a carefully monitored study of fracture growth. And it's a significant issue. And 3D models can be used to reproduce this, but there's a large statistical factor in how this develops because it depends on the details of the fractures placed before the next fracture and how they grew, and also on the rock properties and stress field, which can vary with depth and with position. So we never can measure all of those things accurately enough to be able to completely model it. We can sort of statistically model it and then say, design our array so that on average, we get preconditioning coverage that is sufficient. And finally, I wanted to talk about a case which shows the effect of reorientation from a fracture that breaks down axially and then grows transversely in a rock. In this case, it was, again, a thick sandstone, strong roof above a coal seam. And let me go back to that. We measured by overcoring. This was a project done between CSIRO and SCT again when I was at CSIRO. And the stresses were about balanced as far as the minimum and the intermediate principal stress. They were something like 4 for the vertical stress, the minimum stress. Well, the minimum stress was actually the subhorizontal stress, and it was about 3.8. And I think the subvertical stress was about 4. So it was actually sigma 2. So we thought we would end up perhaps with subvertical fractures at this location. As it turned out, we ended up with subhorizontal, but these stress measurements were the best we had as far as trying to prejudge what we would get. But in order to better understand what we might obtain, we had a stress change cell located here. The sandstone was located here. I should say this is a vertical section showing the fracturing hole on the left and a very close by borehole N2187 located 1.6 meters away, as shown here. And then a second monitoring hole located here and a third monitor hole with a stress change cells located in it, located as shown on the far right. And 2 fractures were placed, one at 160 meters and one at about 170 meters. And we monitored them with a piezometer installed in N2187, a couple meters away, which was located in a sand-filled borehole that was then grouted above it to seal it in. And we also monitored with the other monitoring holes. So we had microprac measurements, which agreed with the overburden, the vertical stress inferred from the density log, more or less, but didn't give us any information that was useful about maximum or intermediate stresses. And after, before and after fracturing in this borehole, we ran an acoustic televiewer log to look at the borehole condition. And you can see here a comparison between the before and after fracturing case at 160 meters. And you can see the after image of the breakdown. The fracture here has multiple strands and is oriented subvertical with striking at approximately north-south, which agreed with the overcore measurement for sigma 1 direction, but has produced a complex fracture shape at the borehole wall. And here's the pressure record from the treatment at 170 meters, which shows high injection pressure. The injection pressure is in red, and that's the surface pressure measured at the pump. And the injection rate is blue, measured in liters per minute. So here's 400 liters a minute, about 2.5 barrels a minute. And here is 250 liters a minute, about 1.5 barrels per minute. This was cross-linked gel, borate cross-linked gel after the initial breakdown and after we got the pressure reduction that initially occurred. But it was touch and go at the start because our main pump was only capable of generating 20 MPa pressure. So during this period, we weren't sure if we could continue this treatment or not. Luckily, we did see a somewhat rapid decrease, but when you're out there pumping for 15 minutes with no change, this later decrease isn't obvious that it's going to happen. But we did record pressure in the offset well, which was located 1.6 meters away, maybe 2 meters at depth. And it showed from early on, from the first intersection, really, a pressure that was basically normal, just above the minimum stress as expected from overcoring and from density log. So this confirmed that all of this excess pressure was due to tortuosity near the wellbore, which eventually was removed by pumping through it, and we then could start proppant and place a couple tons of proppant into the fracture, again with little effect on the bottom hole pressure as recorded at the piezometer. And we determined from stress change data that this fracture was dipping at approximately 35 degrees to the east. And here's a laboratory case also showing another case where a breakdown occurred. In this case, we wanted to produce a horizontal fracture in this acrylic block, but instead it broke down up behind the wellbore or the casing and produced a fracture that then reoriented. But you can see multiple petals of fracture formed and very complex fracture geometry around the wellbore, hence leading to high injection pressures. And the solution to that for us was to develop a way to abrasively cut slots into the borehole at the location where we want the transverse fracture to initiate, so we could produce a fracture with the desired orientation and at the desired location in the straddle interval, because the straddle leaves about 0.5 meter of pressurized open hole. So this localizes the initiation point. And here are my conclusions, which I think I'll leave for you to read. And with that, we can go to questions, if there are any.
Thank you, Rob. I think the questions will start to come in. Bojang wanted to know, is the proppant used only for monitoring, or does it also enhance the preconditioning?
The proppant in the mine backs is used to mark the fracture geometry, because without proppant, we've found it's very hard to find and be sure you're looking at a hydraulic fracture. We have tried to put dye into the fluid, which does work, but it tends to go everywhere. So because it's a molecular size marker, you end up with it all over the face and on the tunnel floor, and then every bit of water. And it's, again, then hard to tell which fracture it came out of and where it came from. But a particulate like proppant ends up being contained to the fracture, and you can then map it. Of course, there is going to be an interaction between the proppant and the proppant placement and where it goes in the fracture. It won't show the very thin branches that might open because it can't get into them, but it does show the main channel. And in the other treatments, like the one I just talked about, we were trying to put proppant in to modify the stress so that we would increase the intermediate horizontal stress or the minimum subhorizontal stress and turn that into a intermediate stress. So then we could produce more horizontal fractures if that was successful. But we weren't really successful in getting enough proppant in to do that at that location.
So the next question, Rob, is from Ben, and he's interested if you've studied hydraulic fracture interaction with natural structures, something like Renshaw and Pollard published on. Or
Yeah,
go ahead. I'm sorry.
We have done quite a lot of work, and when I was at CSRO, we did a lot of laboratory work focused on that issue, propagating fractures through interfaces that were pre-constructed to have a certain frictional strength and orientation and placed ahead of the fracture path, and then carefully in our polyaxial frame, which takes blocks of about 350 to 380 millimeters on a side, we propagate the fractures through them and compare the results to Renshaw and Pollard, another criterion for crossing. And we also had models like Shi Zhang's 2D model that we could use to study the interaction in more detail. And as a matter of fact, there's a series of papers that developed a way to produce 2D laboratory fractures and monitor them optically so we could measure the width and the propagation of them as they interacted with artificial natural fractures. And those were published in ARMA in 2015 and 2017 by myself et al. And James Kerr et al. So if you're interested, you can email me and I can send you citations or copies of those papers.
Thank you. And Saeed appreciated your talk, and he wanted to know whether you considered using fluids other than water, in particular carbon dioxide.
We have considered it, but we didn't want to complicate our life by trying to use a trickier material such as carbon dioxide to do the stimulations. And there was a lot to learn by using a simple fluid like water, or we use linear gel and cross-link gel from time to time, depending on the purpose. But we avoided using compressed gases and supercritical gases and other things like explosive materials because we thought it would just complicate the execution for no benefit that was worthwhile to us.
UMass would like maybe to have you just comment a little bit on what causes the tortuosity. I mean, is it related to stress concentration? Are there other factors that you might advise us on?
I think it's caused by the fracture encountering different structures or features in the rock mass, which can be natural fractures and quite often is for the macro tortuosity effects. The tortuosity near the wellbore is definitely caused by the large stress change that occurs from the first couple radii out from the wellbore, where you have a concentration due to the presence of the wellbore in stress, to the far field stress condition. And as the fracture grows through that, it sees initially one stress field that changes rapidly to the far field, and it rotates to always try to align itself to grow so that it's aligned with the maximum principal stress and opening against the minimum principal stress, and to minimize shear shearing at the tip. And as a result of that, the fracture mechanics says that it produces fracture petals and multiple fracture planes, which is what we see in the laboratory and what we can infer is happening from the scans of the wellbore. So I think that's fairly well understood. But of course, on top of that, there can be other complexity from natural fractures around the wellbore. And in the far field, the offsets seem to be associated with shears or natural fractures. In the laboratory, you can see roughness that's definitely associated with grain size and crystal size in igneous rocks. So the fracture is growing and avoiding or growing through sand grains or quartz crystals in granite material, and you get small scale roughness from that. So basically, any non-homogeneous feature in the rock can produce roughness.
So we need to finish here, but I mean, maybe we'll let a question from an Australian sort of close things out. And Shing from University of New South Wales is interested in just how you decide on the geometries, the spacing of the injection boreholes, and various things along those lines.
Well, a large part is practicality. We have experience now preconditioning in sandstone, conglomerate, and hard naturally fractured rock for metal mining, and have found that 2.5 meters is adequate to precondition the rock. In addition, there has been development of hydraulic fracturing models and cave models that can consider hydraulic fractures, and they have been tuned to what has been seen at mines, and also indicate something in the 2 to 3 meter range seems to be adequate to precondition the rock for large-scale caving. I might mention that the mining industry has started using preconditioning over the last 6, 7, 8 years to reduce large seismic events in the rock mass. So that's another application for hydraulic fracturing that the mining industry has found useful.
We still have a few more questions. If people want to send me an email, I'll put you in touch with Rob with your questions. But thank you, Rob. Outstanding talk. Really very enjoyable. And
no problem. Thank you for having me participate in this.
Yeah,
Thank you, Rob.
you're getting a lot of kudos.
Thanks, Rob. Good to see you again.
Yeah, same here.
Yeah, Ed had a question, but or a comment, and he can interact with you directly.
He might be wanting to say a lot of that work was sponsored by Schlumberger, the laboratory work, and we thanked them for that when I was at CSIRO. And of course, the mines all contributed money and personnel and engineering to all of the field projects that are undertaken, and I thank them for their support as well.
Rob, good job. Enjoyed your presentation. Thank you.
You're most welcome. Thank you.